Hello and welcome to this talk on the comparative design choice analysis for color refinement algorithms beyond the worst case. I am Florian Wetzels from TU Kaiserslautern, and this paper was joint work with Markus and Pascal Schweitzer. So as a start, I will shortly explain what color refinement actually is. Color refinement is a complete but not sound test for graph isomorphism. So now let's look at an example. Here we are given two graphs and want to check whether they are isomorphic or not. An intuitive approach could be to look at the degree sequences of the two graphs. But in this example, they are both the same. Both graphs have 2 degree 4 vertices, one of degree 3, one of degree 2, and 5 leaves. However, there is an important difference. In the left graph, the 2 degree 4 vertices both have a degree 2 and a degree 3 neighbor. In the right graph, one has a degree 2 neighbor and one only a degree 3 neighbor. Color refinement is an algorithm that captures exactly this kind of reasoning to distinguish two graphs that are not isomorphic. Okay, so how does color refinement actually do this? Color refinement partitions or colors the vertices of a graph in an iterative manner. We start with a monochromatic coloring. Then we distinguish the vertices by the number of neighbors in each color. In the beginning, as we only have one color, we just partition or color them by their degree. In the next step, we do this, for example, for the red class. So for each vertex, we count the red neighbors. And now the blue class would be partitioned. Now we do this, for example, for the yellow class, which would split the red class. And in the last step, we do this for the orange class, which would split again the blue class. And then we get our final coloring. This coloring is some kind of fingerprint for the graph. If we compare this to the outcoming coloring for the second graph from the beginning, we can now see that the appearing colors are different, and therefore the two graphs can be distinguished by color refinement. Okay, so why are we interested in a precise analysis for some heuristic for graph isomorphism? Well, color refinement may not be a sound test for graph isomorphism, but it can distinguish most pairs of non-isomorphic graphs. It is also complete, so it never distinguishes isomorphic graphs. Another important property is that the resulting partition is an over-approximation of the orbit partition. Because of this, it is the most important subroutine in practical graph isomorphism solvers. So-called inversation refinement algorithms explore a potentially exponential search tree where at each node a color refinement is performed. Therefore, almost the entire running time is spent in color refinement, so performance is critical, and even small sublinear improvements can have a crucial impact on the performance of the whole tool. Color refinement also has other important applications. It is, for example, used in machine learning, specifically in Weis-Lehmann graph kernels and graph neural networks. Here, performance is of course also important for good scalability. It is also used in linear algebra for size reduction of linear equation systems. Now I will shortly recap what we know about the performance or the complexity of color refinement. First, it can be implemented in time O of m log n. There is also a lower bound of m log n, which was shown under reasonable assumptions in 2017 by Breckholz et al. However, there are many graphs on which color refinement only needs linear time, which should be exploited in practical algorithms. Current implementations are indeed very fast, which they achieve by highly optimized code and treating many special cases with tailored code. What is missing, however, is a precise theoretic analysis within the spectrum of possible running times. So we do not know, for example, if current implementations always use only linear time when it's possible, or if there are certain strategies that are better on specific graphs or worse on specific graphs. Therefore, we need a deeper understanding of the theory of color refinement to answer questions like the following. How do different strategies or design choices compare on non-worst case graphs? Or is there even an asymptotically optimal implementation for all graphs? Based on these questions, we provide the following results in our paper. First, we define two models for comparing different color refinement strategies, an online model and an offline model. Then, we give non-optimality results for any algorithm in both models. And lastly, we do a comparison of specific design choices in practical algorithms, namely the used worklists. To be more precise, we show that there is actually no optimal color refinement implementation within our models, so the considered design choices are a complex problem with no definite answer. We will also use the here listed contributions as an outline for the rest of this talk, and begin with the definition of the two models. But first, we have to recap some basic notions on practical color refinement implementations. The first thing to look at is an improved refinement process. In the example at the beginning, we computed the degree per color for each vertex in every iteration. As there can be a linear amount of refinement steps, this can result in a quadratic or even worse running time. Therefore, we have to use a different algorithm. We now consider a refinement of a single color class, or a union of color classes, with respect to another union of color classes. We show this on an example. In this example, we want to refine the green class with respect to the blue class. For this, we only consider edges between the two sets. Then, we partition the green class by the number of incident edges to the blue class. We get 3 new classes. In the next steps, we then need to do the refinements with respect to these new classes. Therefore, we put them into a work list of classes that we need to handle. It is important to note that one of the new classes can be dropped. This step is important to achieve the running time of m log n by dropping always the largest class. Now it remains to decide in which order the refinements should be performed, or which work list should we use to manage the remaining color classes. This is exactly the design choice we want to investigate. Possible work lists could be stacks, queues, priority queues, or combinations of those. But we also want to define a general model. Towards this goal, we apply 2 approaches. First, in an offline model, we consider algorithms that compute the sequence of color refinements beforehand based on the given graph. In an online model, we consider algorithms that only use the information gathered in previous refinements to determine the next pair. Interestingly, both models come to the same conclusion that there is no asymptotically optimal algorithm. In order to compare 2 implementations or algorithms, we also need a cost model. Here we use the one from the lower bounds proved by Wetzels et al. Intuitively, for refining a class C with respect to a class R, you need to count all the edges that connect the 2 classes. So we assign this number as the cost of one refinement operation. This is a reasonable model, since all color refinement algorithms we know do work within this model, and it seems hard to think of any other way. The total cost of the color refinement process is then the sum of all refinement operations. This means we do not charge the management of the work list. Before we start with the online model, we need one last preliminary ingredient, the quotient graphs. We can define them for a stable coloring, so the output of a color refinement algorithm. In a stable coloring, all color classes have regular connectivity. This means, for example, in the graph on the right, all vertices in the green class have the same amount of red neighbors and vice versa. The quotient graph then represents the color classes and exactly this regular connectivity. The classes of vertices in the quotient graph are labeled with their size, and the edge labels represent the number of neighbors each vertex in a class has in another class. In this example, we omitted the edges with label 0, so between classes that are not connected in the original graph. You can also see that the quotient graph includes self-loops. Here you can see the formal definition of the quotient graph, with the vertex set, edge set, and both label functions we have discussed before. The vertex set is just a set of appearing colors. The edge set is just all possible edges, including self-loops. The vertex labels are the size of the color classes, and the edge labels are the connectivity numbers. For the online model, we now generalize quotient graphs to arbitrary states of the color refinement process, not just the final state. With that, we want to model the on-the-fly available information. Each split or refinement operation contributes information about the regular connectivity between classes. Because we need this information also for unions of color classes, we extend the quotient graph vertices from color classes to all unions. We call this the partial quotient graph, as it only contains the regular connectivity at a specific point in time. Because we consider unions, it is exponential in size. You could also see this as a model for the history of performed refinements. With the partial quotient graphs, we can now define a color refinement strategy. A strategy is a function that takes the history of partial quotient graphs and assigns the next pair of classes to refine with. Based on this definition, we want to answer the following questions. Is there a strategy that gives the optimal running time on all graphs? And, within the practical strategies or work lists, are there some that are always better than others? Here we should note that classical work lists, like stacks or queues, are of course contained in this model. Now we define the second model, which can be seen as in some way orthogonal to the first one. We consider the following problem. Given a colored graph, what is the cost optimal sequence of refinements such that the coloring becomes stable? Here, we do not charge the cost of performing the refinements, we just consider the computation of the optimal sequence. In contrast to the online model, we compute the sequence beforehand, using full knowledge of the graph, and not only the information available from the color refinement itself. Because we are interested in the asymptotic cost of the sequence, we then ask for the complexity of approximating the optimal sequence by, for example, a constant factor. Okay, so now that we have defined the two models, we want to answer the question for an optimal algorithm in the next steps. We start with the online model. Therefore, we now want to prove that there is no strategy within the online model that reaches the asymptotically optimal cost on every graph class. To do this, for an arbitrary strategy, we define a graph class on which it performs logarithmically slower than the optimal solution. To construct adversary graphs for any algorithm within the online model, we first have to understand how the worst-case behavior can actually appear. In a second step, we can then try to enforce this behavior for specific strategies. So we start with the construction of a m-log-n graph. For this, we want to partition a vertex set in a logarithmic split scheme to get log-n manual refinements that all have linear costs. Therefore, we consider sets of size 2 to the k. In the example on the right, you will see the steps for k equals 3. As a first step, we want to split the set x in halves, which is induced by a separated pair of vertices. Then the halves of x should induce the continuation of the split scheme, so that the next pair, which then partitions x into its quarters. Now the quarters of x split another pair that causes x to be split in eighths. For larger k's, we would continue this for k many rounds. The graph class is then extended to the size 2 to the k times k squared. We do this by extending x to 4 layers, where the two middle layers contain a full bipartite graph of size k for each vertex in x. Then there are 2 to the k times k vertices and 2 to the k times k squared many edges in these layers. The reason why we do this is that we later want to insert gadgets without increasing the asymptotic size of the graph. Now we look at the slow behavior of the color refinement on these graphs. First, x is split in halves by the first pair. Then we continue with one of the two halves, as the other one is dropped by the algorithm as discussed before. The split propagates through the different layers and then causes x to be split in quarters. Until now, we have costs of roughly 2 to the k times k squared. Out of the 4 quarters, we take 2 to continue with. Let's assume that we proceed in a breadth-first manner, so both quarters are propagated through the layers. Then we get again 2 to the k times k squared costs for this second round. Now that x is partitioned into eighths, we again continue with 4 of these parts and get again 2 to the k times k squared for the third round by a BFS approach. If we repeat this for k many rounds, the total costs are 2 to the k times k to the third, which is m log n. Now we'll show you that the worst-case behavior is not necessarily enforced on this graph class. The reason is that a depth-first approach can lead to linear running time. We start in the same way as before. The first round has cost of 2 to the k half times k squared. For the second round, however, we do not continue with both quarters, only with one. This gives costs of 2 to the k divided by 4 times k squared. In the third round, we get 2 to the k divided by 8 times k squared by a DFS approach. Now the first layer x is fully individualized, and we have total costs of 2 to the k times k squared until now. Only the one last sweep through the layers is needed, which keeps linear costs. It is possible to enforce the worst-case behavior by adding gadgets instead of the simple pairs that continue through the different rounds. For the lower bound construction, we would insert so-called AND gadgets that need all quarters, eighths, and so on to be split in order to be activated and to continue the next refinements. But we want to construct adversary graphs for specific strategies, so we need other gadgets, which I will show you now. The first gadget we need is the unidirectional gadget. As the name suggests, it propagates the split in one direction, but not in the opposite direction. Specifically, if we look at the graph shown here, separating the A' vertices causes a split on the A vertices, whereas separating the A pair does not lead to a split of the A' vertices. The reason for this is that the right part of the gadget is the CFI gadget or the N2 gadget from the lower bound paper. And the A' pair is connected to it such that it activates both input gates upon the split. For those who don't know these gadgets, let's look at what happens after separating the left pair. We can see that A0 has two orange-blue neighbors, whereas A1 has a pure orange and a pure blue neighbor. Therefore, they will also be separated. On the other hand, after splitting the right pair, we see that A'0 and A'1 both have two orange-blue neighbors, so they won't be separated. We now use the unidirectional gadget for the core gadget of our construction, the concealer gadget. A concealer gadget of order I consists of I unidirectional gadget whose A pairs are all connected to a new pair of out vertices. So activating unidirectional gadgets would lead to a split of the out vertices. However, we then modify the graph in the following way. All but one unidirectional gadget are changed so that the connection of the A prime pairs is equivalent to the connection of the A pair. This means that separating these vertices does not cause an activation of the concealer gadget. To cause a split of the output pair, we need to separate one specific input gate, which is highlighted in green. The other pairs can be seen as dead ends. Note that there are I different concealer gadgets of order I. The crucial property is that all concealer gadgets look the same from the outside. Formally, we mean that the quotient graphs of all concealer gadgets of the same order are equal. Let's assume that an online strategy picks pair X as the next class to refine. Then we can exchange the gadget such that X is a dead end, but the strategy will still pick X next, as it only uses the quotient graph for its decision. If we now insert the concealer gadgets in the worst case graph class, we get a new graph class with the same properties as before. There is a strategy for every graph that only needs linear costs. We can achieve this by always picking the right pair of the concealer gadget and else following the depth-first approach from earlier. Also, for any strategy, there is a graph class on which it needs cost of m log n. We can build such adversary graphs by swapping the concealer gadgets until for each round the BFS behavior is enforced. With this knowledge, we can now conclude our main theorem. For any strategy of the online model, there is an infinite graph class on which it performs logarithmically slower than the optimal strategy. Okay, so with this theorem, we can check the second point for the online model, but we still have to do the same task for the offline model, which we will do now. First, recall the definition of the problem for the offline model. Given a colored graph, compute a valence sequence of refinements such that executing the sequence leads to a stable coloring and the sequence is cost optimal within all sequences of this property. We call this the refinement worklist problem. We were able to show that this problem is NP-hard. However, we are also interested in the question for an asymptotically optimal sequence, so approximating the optimal cost by a fixed constant factor would also be a good solution. In fact, we could show that this is also not possible with a tractable algorithm. Unless p equals np, any polynomial time algorithm may only reach an approximation factor of log n for the refinement worklist problem. We have shown these results by reduction from the set cover problem. We have now completed the main results of our paper. As a last step, I will quickly go through the comparison we provided on specific worklists that are used in practice. We begin with the comparison of queues and stacks. Earlier, we have already seen a graph classes on which a stack can outperform a queue by a logarithmic factor. It is also possible to construct a graph on which the opposite is true. We can use AND gadgets to force stacks and queues in specific behaviors, such that certain splits happen earlier for one of the two options. Here you can see the queue graphs. This construction basically uses the same gadgets as the lower bound graphs and our concealer gadgets. On the left is the starting gadget that is built around an AND gadget. In the middle, we can see unidirectional gadgets, and on the right is the lower bound graph using AND gadgets. Some practical implementations use combinations of a stack worklist with some sort of priority-based strategy. Therefore, we also consider priority queues ordering classes by size. We were able to show that neither min nor max priority queues could outperform each other or stacks or queues consistently. Again, the difference could be logarithmic. Summing up our results, we were able to show that there is no optimal strategy or design choice within current color refinement algorithms, under the assumption of the two defined models. The relationship between the two models and the similar conclusions led us believe that the existence of an optimal algorithm is unlikely. Given the importance of color refinement practice, we think that our results imply that the choice of strategy for practical implementations is not an easy one and should probably depend on the application. We strengthened our theoretic results by showing non-optimality of strategies that are used in practice. Thanks for your attention, and I'm looking forward to see you in the discussion.